Imagine a user is on your application and, they decide to update their profile picture.
Right.
Simple enough, right? I mean, they upload the image, they hit save, and somewhere on your server, a database record updates.
Exactly, just a standard request.
But because of how your API is wired, that simple profile picture update accidentally triggers a database listener.
Oh yeah, the ripple effect.
Right, which fires off an event, which wakes up some ancient legacy service, and suddenly your automated warehouse is shipping a pallet of televisions to an address in Ohio.
It sounds impossible.
Yeah.
But honestly, it happens every single day in enterprise software.
And it almost always traces back to four little letters, right? CRUD. Create, read, update, delete.
Yes, CRUD. It is basically the silent killer of large-scale system integrity.
Wow, silent killer. Strong words.
Well, I mean, it is. We build these massive, highly complex business domains, and then we expose them to the outside world using the exact same generic vocabulary we'd use to manage, like a simple spreadsheet.
So we're reducing complex business intent down to mere data mutation.
Exactly.
Yeah.
You lose all the nuance.
Which brings us to exactly what we are unpacking today. Welcome to the deep dive, by the way.
Glad to be here.
Today, we are looking at a highly advanced premium architecture model for building high-performance APIs, specifically within the Symfony framework.
And just to clarify, this isn't about setting up a quick weekend project.
Definitely not. If you are an engineer prepping for a big system architecture meeting or, a tech lead trying to untangle a monolithic nightmare.
Or honestly, just someone who wants to understand how massive platforms manage thousands of requests a second without complete chaos.
Exactly. This deep dive is for you. We are going to tear down the traditional REST API model and replace it with an operation-oriented engine.
And the fundamental shift here is moving away from this idea of an API as a passive storage facility.
Like a place where you just push and pull data.
Right. We want to turn it into an active, highly regulated, intelligent processing engine, where every single action has a strict contract.
Okay, let's get into the weeds on this. Because if I'm a developer and you tell me CRE is broken, I'm going to push back.
Sure, that's fair.
I mean, CRUD is incredibly fast to build. Almost every modern framework, Symfony included, has tooling that can generate a standard CRUD API over a database table in like 5 seconds.
Yep, the maker bundles are super fast.
So why are we throwing out 20 years of standard practice? Let's take the classic e-commerce example. I have an order, I want to approve it.
Okay.
In a traditional REST API, I'm sending an HTTP PassCH request to something like /AP/v1/orders/123.
Exactly. And your JSON payload in that request is usually just a very simple key value pair.
Right, I just send status::approved.
Yeah. You are targeting a specific entity, the order, and you're just mutating one of its properties.
And from a pure data perspective, that works, right? The database updates.
It updates, sure.
Yeah.
But what we're saying is that at an enterprise scale, this approach completely masks the actual business intent.
Wait, so the problem here is ambiguity.
Massive ambiguity. It creates a dangerous layer of guesswork.
Because when the server receives that status::approved JSON, it has to guess what you actually want it to do.
Exactly. The system is forced to infer the user's intent purely based on that one property change.
I see. So it has to say, okay, does changing this string to approved mean I need to initialize a payment capture through Stripe?
Right. Or does it mean we need to call the warehouse API to reserve physical inventory?
Or do we trigger an email via SendGrid?
Exactly. The intent is hidden.
So we're basically walking into a kitchen, looking at the chef and saying, make the ingredients hot.
That is a perfect analogy.
Yes. We aren't giving them a recipe. We aren't saying bake a cake or boil pasta.
Right. It's describing a state change.
Right. And we're relying on the chef to just guess what we actually want based on the fact that we turned the oven on.
That is exactly the dynamic. And architecturally, this leads to what we call scattered logic.
Scattered logic, meaning it's just everywhere.
Yeah, because the API controller just receives a status string. The actual business logic has to live somewhere else.
Right, because the controller doesn't know about Stripe or the warehouse.
Exactly. So developers end up putting it in massive, bloated controller methods, packed with, like, dozens of if statements.
Or worse, they use database entity listeners.
Oh, man. Doctrine entity listeners.
I have nightmares about those.
They are tricky.
For those who might not have had the pleasure, this is when you attach code directly to the database lifecycle, right?
Yeah, deep down in the ORM layer.
Right, so some piece of code notices, hey, The status column just changed from pending to approved?
And it suddenly decides to fire off an HTTP request to a third-party billing service.
Which is
It
terrifying.
is the ultimate anti-pattern for maintainability.
Okay.
The side effects are completely invisible.
Because a new developer looking at your API endpoint just sees a simple data update.
Right. They have no idea that changing that one field triggers a cascade of irreversible actions across like 3 different microservices.
Which makes debugging nearly impossible because the causality is totally hidden.
Exactly. You're tracing bugs through invisible tripwires.
All right, I buy that. The ambiguity is super dangerous. So what is the alternative? How does an operation-oriented architecture solve the make it hot problem?
By elevating the intent right to the surface.
Okay, what does that look like?
Instead of passive mutation, you send a standardized HTTP POST request.
Always a post.
Usually, yes. You might point it to a generic endpoint like /epi/v1/operation,
Okay.
but the payload completely changes shape. Instead of sending just the data you want to change, you send a command.
A command? Like what?
So the JSON payload looks like this. Operation is approve order, and data is the ID 123.
Oh, wow. Approve order. It's an explicit verb.
It's an undeniable action.
You are no longer saying, here is some data, please figure out what it means.
Exactly. You are saying execute this exact specific business process.
That makes so much sense.
In domain-driven design, we talk a lot about the ubiquitous language.
Remind me what that is.
It's the idea that the code should speak the exact same language as the business stakeholders.
Right, because a stakeholder never says, patch the order entity's status property.
Exactly. They say, approve the order.
So this architecture maps your API endpoints one-to-one with actual business capabilities.
Yes. And I can see how that fundamentally changes the structure of the code base.
Right, you're moving from controllers that try to manage entities to dedicated handler classes.
Dedicated handlers whose sole responsibility is executing one specific operation.
So you get these self-contained, single responsibility handlers.
Precisely. You have one PHP class called approve order handler.
And all the orchestration, the payment gateway calls, the warehouse reservations, the emails.
Happens right there. Explicitly in the light of day. It's perfectly isolated.
Okay, but this brings up a massive technical challenge.
Lay it on me.
If we are completely isolating these operations, we need absolute strictness about what data comes in, right?
We absolutely do.
Because with traditional CRUD, the framework usually just maps the incoming JSON directly to your database entity.
Right, using forms or serializers.
But if we have a standalone approve order operation, how does the system strictly define what the input should look like before the operation even begins to run?
This is section 2 of our deep dive, defining boundaries and contracts.
Awesome.
We have to establish impenetrable boundaries around our operations. And the mechanism for that is the data transfer object, or DTO.
DTOs. I feel like this term gets thrown around a lot, honestly, sometimes, just to describe any random array of data.
Yeah, the term has been diluted. But here we're talking about something very rigid.
Let's use a specific example from the sources. Send payment input.
Great example. In modern PHP, specifically PHP 8.2 and beyond, you define this as a strictly typed read-only class.
Read-only class. That's a relatively new feature, isn't it?
It is, and it's not just syntactic sugar. It is a profound architectural guarantee.
How so?
By defining the DTO as read-only, you are telling the PHP engine that once this object is instantiated with data from the user, it is mathematically immutable.
Oh, wow. So no other service, no rogue piece of legacy code further down the pipeline can accidentally overwrite it?
Exactly. They can't change the payment amount or swap the recipient ID. It is permanently locked state.
That eliminates an entire category of side channel state mutation bugs.
It really does. But, immutability is only half the battle.
Right, because the data also has to be undeniably valid.
Yes. And rather than writing dozens of lines of procedural if statements inside your handler.
Or like checking if strings are empty, checking if numbers are positive.
Exactly. This architecture utilizes declarative validation instead.
Okay, this is where we use PHP attributes, right? The metadata tags that sit directly above the class properties.
You got it. So for the receiver string property, you'd add the not blank attribute.
And for the amount float, you add greater than 0.
What is happening under the hood here is really elegant. The Symfony validator component reads this metadata via reflection.
Reflection is basically the code inspecting itself, right?
Exactly. It parses these attributes and builds a complete validation tree in memory.
So you are declaring the absolute laws of physics for this specific operation.
I love that phrasing. Yes. You are stating that in your business domain, it is fundamentally impossible for a payment amount to be zero or negative.
And the beauty of this is that the execution engine forces this validation to happen before your business logic is ever touched.
Yes, that's the crucial part.
So if I send a payload with a negative amount, the validator catches it, constructs an error response, and kicks it back to the client immediately.
Exactly. My actual send payment operation class doesn't even wake up.
It doesn't have to waste CPU cycles checking the data.
Right. If the send payment input object successfully reaches your operation handler, you have absolute mathematical certainty that the data is flawless.
So your business logic can just run completely free of all that defensive programming clutter.
It makes the code incredibly clean.
Okay, so we have an ironclad contract for the data coming in. But an API is a two-way street. What about the data going out?
Ah, the output state.
Because if every operation is a unique snowflake, do they all return completely different data structures? That sounds like a nightmare for the front-end developers.
It would be a nightmare, which is why the architecture enforces a rigidly standardized output boundary as well.
Okay, how does that work?
Every single operation, regardless of what it actually does, must return a specific envelope. Usually, this is defined as an AP output class.
And what does that envelope actually contain?
It's highly predictable. It
Yeah.
generally contains a data property, which holds whatever the specific payload is.
Like the ID of the newly created order?
Exactly. And it also contains an HTTP code property, like the integer 200 for OK or 202 for accepted.
So the routing layer, the part of the application that actually talks to the internet, only ever has to understand one single response format?
Precisely. It takes that AP output object, runs it through the Symfony serializer to turn it into JSON, applies the HTTP status code, and sends it off.
That creates a beautifully standardized operation contract.
Every operation is basically an interchangeable gear. They all implement the exact same operation interface.
And what does that interface require?
It mandates one single method, a public function called perform, which accepts mixed data and returns that AP output object.
Wait, hold on. I'm trying to wrap my head around this.
Sure.
If every operation implements the exact same interface and the perform method just accepts mixed data,
Yeah.
how does the system know which specific DTO an operation actually requires?
That's a great question.
Like, how does it know that the send payment operation needs a send payment input object, while approve order needs an approve order input object?
Through operation metadata. This is really the cornerstone of the automated routing.
Okay, tell me more about that.
At the top of your send payment operation class, you define a custom attribute.
Something like operation metadata.
Exactly. It looks like operation metadata, name is send payment, and input is send payment input.class.
Ah, I see. So the operation is basically wearing a name tag.
A name tag with instructions, yeah.
It's announcing to the system, I am the send payment operation, and if you want to run me, you must provide an object that perfectly matches the send payment input blueprint.
Yes. The execution engine reads this metadata dynamically.
So it understands the exact shape of the plug required before it even tries to plug it in.
Exactly. Which is brilliant for abstraction.
It is, but as a skeptic, I have to point out a massive looming problem here. Let's talk about scale.
Okay, let's go there. Section 3, speed and efficiency.
Right, because if I'm building an enterprise application, let's say a comprehensive ERP system for a huge logistics company,
You're going to have a lot of operations.
I might have 600, maybe 1,000 distinct operations.
Yeah.
Generating shipping manifests, calculating cross-border tariffs, updating driver schedules.
That is a very standard scale for this type of architecture, yes.
Okay, but if I have 1,000 distinct operation classes, and each one relies on different massive services.
Like the tariff calculator needing a database connection.
Right. And the manifest generator needing a PDF rendering engine, the email sender needing an SMTP connection.
It's a lot of weight.
So if a user just sends a tiny ping to check their notification count, does the framework really have to load all 1,000 of those operations into memory?
All of them. And all their heavy dependencies.
Yeah. Just to figure out which one to use, because that will instantly crater the server's RAM.
It absolutely would. You've just described the classic memory bottleneck of monolithic dependency injection.
So how do we avoid it?
If you instantiate everything up front, your boot time goes from milliseconds to seconds, and your application falls over under load. The architecture avoids this entirely by utilizing a mechanism called lazy operations.
Lazy operations. Okay, here's where it gets really interesting. Unpack that for me.
Sure. You know, Symfony uses a dependency injection, or DI, container, right?
Yeah, when the application starts, it builds this massive map of every class and service it might ever need.
Exactly. So how do we tell the DI container to hold off on actually building these heavy operations?
Right. How does it know to be lazy?
The mechanism relies on a specific PHP attribute provided by Symfony. Auto-configure with the lazy flag set to true.
Okay, so when you attach this to your operation interface, you fundamentally change how the Symfony container compiles itself.
Yes. Let's go under the hood here.
What actually happens during that container compilation phase?
When you clear your cache and Symfony rebuilds the DI container, it runs a series of compiler passes.
It's scanning the code base, right?
Exactly. It scans your entire code base, looking for classes that implement the operation interface.
But because they are tagged as lazy,
It does not write the PHP code to instantiate your actual calculate tariff class. Instead, it utilizes an internal library to generate a proxy class.
a proxy class, like a stand-in or a body double.
Exactly like a body double.
Yeah.
The container generates a tiny, virtually empty PHP class that implements your operation interface.
But what's inside it?
Almost nothing. It has the same method signatures, but it contains absolutely zero business logic.
How crucially, it asks for 0 dependencies in its constructor.
Exactly. So it weighs practically nothing in memory.
Practically nothing.
So when an HTTP request comes in, the DI container boots up and loads 1,000 of these empty proxies.
And it takes a fraction of a millisecond.
Right. The heavy database connections, the PDF rendering engines, none of them are initialized.
So when do they actually wake up?
They remain completely dormant until the exact microsecond that the execution engine explicitly invokes the perform method on that specific proxy.
Oh, wow.
The moment that method is called, the proxy intercepts the call, turns around to the core container, and says, okay, I actually need to do work now. Give me the real class.
Then it instantiates the heavy dependencies, executes the logic, and returns the result. That is a phenomenal piece of engineering. It's like having a massive warehouse full of complex robotic assembly lines, but they are all just holograms.
I love that analogy.
They take up absolutely no physical space. But the moment you touch one to turn it on, it instantly materializes into solid steel and starts working.
That is exactly what is happening.
Yeah.
It allows you to have the architectural cleanliness
Right.
of a massive monolith with thousands of operations while maintaining the sub-millisecond memory footprint of a tiny microservice.
It's the best of both worlds, but I mean, as you can imagine, managing 1,000 holograms requires a very sophisticated central coordinator.
It does. Which brings us to the central dispatcher.
Right. Because the HTTP request comes in, and the framework needs to figure out which of those 1,000 proxies to route it to.
If the operations are the execution arms, the dispatcher is the air traffic controller.
It doesn't fly the planes, but it strictly dictates which runway they land on.
Exactly. So let's trace the execution flow through this dispatcher.
Walk me through it.
The very first thing that happens when an HTTP request arrives is that it hits an adapter layer.
The controller.
Right. The controller takes the raw HTTP requests, strips away all the transport-specific noise like the headers, the cookies, the query string.
And extracts the pure intent.
Yes. It creates an API input object containing just two things: the requested operation name and the raw JSON payload.
So it's completely decoupling the execution engine from the internet. The engine doesn't even know what a URL is.
Exactly. It just knows it received an envelope.
Okay, what happens to that AP input envelope?
This AP input is then handed to the core of the central dispatcher, typically called an AP operation handler.
And the handler's job is to match that input to the correct lazy proxy.
Yes.
But how does it search through them efficiently without waking them up? Like, if it touches them, don't they materialize?
That's where a mechanism called a tag iterator comes in.
Tag iterator.
During that compilation phase we talked about earlier, Symfony automatically applies an internal tag to every service that implements the operation interface.
Okay.
The AP operation handler injects an iterator of all these tag services. It loops through the proxies, inspecting only their metadata.
Which is readable without instantiation.
Exactly.
So it's looking for the name tag. It checks the metadata attribute until it finds the one where the name matches the requested operation.
You asked for send payment, here is the send payment proxy.
But wait, it still doesn't wake the proxy up, right?
No, safety first. The handler reads the metadata to find out what DTO is required.
It sees it needs a send payment input.
Right. It takes the raw JSON payload, uses the Symfony serializer to map the JSON fields directly into the strongly typed PHP object.
And then it fires a validation engine.
Exactly. Checking the not blank and greater than 0 rules we set up earlier.
And if that validation fails,
the dispatcher instantly throws an HTTP 400 bad request exception.
which means the malicious or malformed request is rejected. and the heavy proxy remains completely asleep.
We've protected the server's CPU and memory from having to deal with garbage data.
It is extreme defensive programming. I love it.
Only if the DTO is perfectly valid does the dispatcher finally hand the object to the proxy, call perform, and trigger the actual business logic.
Okay, I am fully sold on the execution engine. The isolation, the lazy loading, the strict validation, it's incredibly robust.
It really is.
But let's zoom out a bit for section 4, routing topologies.
Let's do it.
Because we've built this pristine transport agnostic engine that only speaks in AP input envelopes.
Right.
But how do we actually get the HTTP request to it? Because front-end applications and external partners still need to make HTTP calls to URLs.
Because the engine is completely decoupled from the transport layer, your Symfony controllers are no longer running business logic.
They are strictly adapters.
Exactly. Their only purpose is to take an HTTP request, format it into an APN input, hand it to the dispatcher, and then format the AP output back into an HTTP response.
Right, it's a classic hexagonal architecture concept, ports and adapters.
The core domain is totally isolated.
So the HTTP controller is just one of many possible adapters. I could theoretically trigger these same operations from a CLI command or a message queue without changing a single line of business logic.
Precisely. And in terms of HTTP adapters, there are 3 distinct routing topologies you can deploy depending on your organizational needs.
Let's walk through them. What's the first one?
The first and purest is the single entry point.
This one is wild to me. The idea is that your entire API has exactly one URL, like post/ap/v1/operation.
Just one. Every single request, whether you are creating a user, deleting a post, or calculating taxes, goes to that one exact endpoint.
It simplifies the routing matrix completely, I suppose.
It does. The client sends a post request, and inside the JSON body, they specify operation:create user.
And in Symfony, you can map this incredibly cleanly using the map request payload attribute on the controller.
Which automatically deserializes the incoming JSON directly into your base AP input object.
I love the efficiency of it, but I can hear front-end developers screaming from here.
Oh, absolutely.
Because if you have a massive React or Vue application, debugging network tabs in the browser becomes a total nightmare if every single network request just says POST/operation.
You can't see what's happening at a glance. It's a very valid operational critique.
Plus, it makes things like CDN caching or API gateway rate limiting way more difficult, right?
Yeah, because those tools usually rely on distinct URLs to differentiate traffic.
So what's the solution?
That's why the second topology exists, the slug adapter.
Okay, how does the slug adapter fix the visibility issue?
Instead of putting the operation name deep inside the JSON body, you expose it in the URL structure.
So you configure a dynamic route like post/epi/v1/operation/curly brace operation slug.
Exactly. So the URL actually looks like /AP/v1/operation/approve order.
Okay. And the controller adapter extracts that operation slug from the URI parameters.
It translates approve order to the formal approve order operation name, constructs the AP input, and passes it to the dispatcher.
And the JSON body now only contains the actual data payload.
Exactly.
This feels like the perfect middle ground. You retain the unified pipeline of the central dispatcher, but you give your network monitoring tools and front-end engineers distinct URLs to track.
It's the most common approach for greenfield projects.
But let's throw a wrench in this.
Go for it.
Let's say I'm an enterprise tech lead. I have a massive 5-year-old API built on traditional CRUD endpoints.
A very common scenario.
I have 30 external B2B partners who have hard-coded integrations with patseh/ap/v1/inventory/id.
Right.
Now, I want to migrate to this new operation-oriented engine because my internal logic is a total mess. But I cannot legally force 30 partners to rewrite their integrations overnight. What do I do?
You implement the third routing topology.
The hybrid approach.
The hybrid approach.
This is how you migrate massive legacy systems without downtime.
Okay, how does it work?
You leave the traditional REST endpoints exactly where they are. You still have patseh/ap/v1/inventory/id.
But the controller behind that endpoint completely changes. Right. It becomes a facade. The external partner sends their standard patseh requests with status reserved.
And your legacy controller receives it.
But instead of executing doctrine queries or calling services directly, the controller acts as an invisible translator.
Oh, I see. It extracts the ID from the URL, takes the status from the payload, and internally it manually constructs an AP input object.
It says, okay, the partner thinks they're doing a generic pay TCH, but But in our new system, this translates to the reserve inventory operation.
It creates the DTO, sets the ID and the status, and drops it right into the new central dispatcher.
Exactly. To the outside world, absolutely nothing has changed. The contract is fully preserved.
But internally, you have completely rerouted the execution through your highly structured, perfectly validated, operation-oriented pipeline.
You can gradually strangle the legacy code base, upgrading the internal plumbing without ever changing the public-facing faucets.
That is the kind of pragmatic architecture that saves millions of dollars in migration costs.
It's a lifesaver.
But speaking of enterprise realities, we need to move on to Section 5, fortifying the engine. We need to talk about armor.
Yes, security. Because a beautifully structured engine is useless if it gets instantly taken down by a DDoS attack.
Or compromised by a privilege escalation bug.
Exactly. Security in a system like this cannot be an afterthought. It has to be baked into the very topology of the request lifecycle.
We refer to this as the layered lock.
Right. Security is divided into two, which is terribly slow and incredibly difficult to scale across multiple servers because they all have to share that session storage.
A stateless authenticator, conversely, remembers nothing.
Nothing at all. Every single request must independently contain the cryptographic proof of identity.
Usually this means passing a JSON Web Token, or JWT, in an XAuth token or authorization header.
And the beauty of a JWT is that the server doesn't even need to query the database to know it's valid.
If implemented correctly, yeah, because the JWT contains the user's ID and roles, and the entire token is cryptographically signed by the server.
Right, using an HMSE or RSA algorithm. So when the token arrives, the authenticator simply recalculates the signature using its secret key.
And if the signature matches, the token is undeniably authentic.
It guarantees the user is who they say they are, entirely in memory, in microseconds.
And if the signature fails or the token is missing,
The firewall instantly bounces the request. A 401 unauthorized response. The routing layer is never touched. The dispatcher is never invoked.
but authentication proving who you are is only perimeter 1. Perimeter 2 is authorization.
Answering the question, are you allowed to do this specific thing?
This is where the operation voter comes in. And this happens much deeper in the life cycle, right?
Yes. The dispatcher has already validated the DTO and is holding the lazy proxy ready to execute.
Right. So just before calling perform, the dispatcher explicitly invokes Symfony's authorization checker.
A calls is granted, passing in perform and the specific operation object.
This hooks into Symfony's security voter system. But let me ask you this. Why use a separate voter class?
What do you mean?
Why not just put an if statement right at the top of the approve order operation that says, if user has role ADMN?
Separation of concerns. The approve order class should only contain the business logic of how an order is approved.
It shouldn't care about the corporate hierarchy of who's allowed to push the button.
Exactly. By externalizing authorization into a voter, you create a dedicated class that inspects the current user's roles, inspects the requested operation, and applies complex matrix logic to determine access.
It's a granular, role-based access control system that sits completely independent of the execution logic.
It keeps the business logic pure.
But security isn't just about bad passwords and permissions. It's about volume.
Traffic control.
Right. What happens if a legitimate user writes a terrible script that accidentally sends 5,000 legitimate requests a second?
That brings us to rate limiting. High-performance architectures universally rely on algorithms to protect their resources.
And the most effective of these, and the one implemented in this blueprint, is the token bucket model.
I love the token bucket algorithm. It's so elegantly simple to visualize.
Let's walk through it for the listener. Imagine a literal bucket sitting in memory. This bucket has a maximum capacity, let's say 5,000 little wooden tokens.
Okay. Every time an HTTP request enters the system, at the absolute earliest possible moment during the kernel events request phase, the rate limiter reaches into the bucket and attempts to remove exactly one token.
If the bucket has tokens, you take one, and your request is allowed to proceed to the firewall.
And if the bucket is empty?
You are immediately rejected. The server returns an HTTP 429 too many requests status code and shuts the connection down.
Meanwhile, independently of the request, there's a constant drip refilling the bucket.
The source mentions a specific rate. Let's say it adds 200 new tokens every 20 minutes, up to the maximum cap of 5,000.
So if I haven't used the API all day, my bucket is full. I have 5,000 tokens. I can suddenly burst 5,000 requests in a single second.
The system handles it seamlessly. You get your data fast.
But if I try to send request 5001,
You hit a wall. And you can't burst again. You have to wait for the slow drip to give you more tokens.
It perfectly balances the need for burst capacity with the necessity of sustained traffic throttling.
Now, technically, implementing this across a distributed cluster of servers requires atomic operations.
Right, you can't just use a SQL database and do select token count, subtract 1, and update.
Because if 10 requests hit at the exact same millisecond, they all read the same count, and you get race conditions.
Exactly. You'll let more traffic through than you intended.
So this is typically backed by Redis.
Redis runs in a single thread and guarantees atomic operations. The rate limiter uses a Redis command like decr to decrement the token count,
It is mathematically impossible for a race condition to occur.
ensuring your rate limits hold absolutely firm, even under massive concurrent assault.
That is serious enterprise armor. But I want to talk about another form of armor, one that protects the integrity of the data itself. Because we talked about DTO validation earlier, making sure amounts aren't negative. But what if the rules of validation need to change based on who is asking?
Oh, validation by role. This is a highly nuanced feature, and it solves a massive headache in organizational software.
Let's use a real-world scenario. Let's say we have an operation to update a massive project timeline.
The input DTO is complex. It has dozens of fields.
Right. And two different users send the exact same JSON payload to update the project. One user is logged in as role project manager. The other user is logged in as role developer.
With dynamic validation by role, the Symfony validator intercepts the DTO and inspects the user's security context before applying the rules.
So for the project manager, it dynamically applies a specific validation group.
It dictates that the start date field is strictly required. It enforces a not blank attribute.
And if the manager forgets to include a start date,
The system kicks back an error because establishing timelines is their core responsibility.
but when the developer sends the exact same payload, the validator applies a different group.
It knows a developer shouldn't be altering project timelines. So for the role developer, that exact same start date field becomes strictly forbidden.
It dynamically enforces an is-null constraint.
Exactly. So even if the developer accidentally includes a start date in their JSON, maybe because the front-end application has a bug and submitted a cached value, the backend actively rejects it.
It says, you are a developer. You do not have the authority to even touch this field, regardless of whether the date is formatted correctly.
It is an incredibly powerful paradigm. You are enforcing complex organizational hierarchy and business rules without writing a single procedural if statement in your controllers.
The validation layer inherently distrusts input and molds its defense mechanisms around the identity of the actor.
There is one final layer of defense we need to cover: contextual isolation.
Because if you have an API with hundreds of endpoints, maybe powering 3 entirely different domains within a massive corporation,
Like e-commerce, human resources, and warehouse inventory.
how do you ensure that traffic doesn't accidentally cross streams?
The risk of operational cross-contamination is high in vast enterprise APIs.
You absolutely do not want an internal routing glitch to allow a payload meant for the send payroll operation to execute via a public-facing e-commerce endpoint.
To prevent this, we use domain-driven design-bounded contexts enforced via a kernel interceptor.
So an event subscriber that listens very early in this Symfony request lifecycle.
Right, when you define your routing adapters, you tag them with custom attributes declaring their context.
For example, your warehouse endpoints are tagged with Operation Context Inventory Management.
And your checkout endpoints are tagged with Operation Context e-commerce.
And your operations themselves also declare which context they belong to.
Exactly. The kernel interceptor acts as a strict border patrol agent. It inspects the route the user hit, looks at the context tag, and then inspects the specific operation the user is trying to execute.
If a user sends a payload asking to run the send payroll operation, but they send it to a URL tagged as inventory management,
The interceptor immediately throws a 403 invalid context for operation exception.
it's like having distinct color-coded security badges for different floors of a high-security building.
Even if your JWT is perfectly valid and gets you through the front door, if you try to use a blue warehouse badge to open a door on the green finance floor, the system just rejects you at the hardware level.
The operation doesn't even run.
It guarantees that your domains remain perfectly segregated, even if they share the underlying central dispatcher engine.
Okay, we have built an absolute fortress. The engine is fast, it's strictly validated, and it's impenetrable.
But we need to address the reality of time.
Right, section 6, the temporal dimension. Because in any complex system, tasks vary wildly in how long they take to complete.
And this is where most APIs either succeed at scale or completely collapse.
Let's face it, updating a user's display name takes about 2 milliseconds of database time.
But generating a 60-page PDF invoice, rendering graphs, saving it to an S3 bucket, and emailing it to a client, that might take 5, maybe 10 seconds.
And in the world of high-performance APIs, tying up a server thread for 10 seconds is a catastrophic failure.
Because PHP FPM, the process manager that handles requests, only has a limited pool of worker threads available.
If 50 users ask for PDFs at the exact same time, all your worker threads get blocked waiting for the PDFs to generate.
And when thread 51 comes in just wanting to load the homepage, the server is out of workers.
The site hangs. The entire application stops responding to everyone simply because 50 people are waiting for an email.
The engine must adapt to the temporal weight of the underlying business logic. It has to cleanly separate synchronous execution from asynchronous execution.
To understand how it handles this, we can look at an execution strategy matrix across 4 key categories.
Let's break down the first category, response time.
Okay, for synchronous operations, the lightweight tasks, the execution blocks the HTTP thread.
The client waits. The operation runs, finishes, and returns the result in a few milliseconds.
But for heavy asynchronous tasks, the response time is fundamentally altered.
The central dispatcher realizes the operation is marked as async, and it immediately returns an HTTP 202 accepted response to the client.
A 202 accepted. It essentially means, I received your request, it is valid, but I am not done processing it yet.
The response time drops back down to sub-milliseconds, but the work hasn't actually happened.
My favorite analogy for this is the dry cleaner versus the grocery store.
Oh, I like this one. Synchronous is the grocery store.
Right. You hand the cashier your money, and you stand there, blocking the line, waiting for them to count the coins and give you your exact change right then and there.
And asynchronous.
Asynchronous is dropping your suits off at the dry cleaner. You don't stand at the counter for 2 straight days watching them wash your clothes.
That'd be weird.
You hand them the bag, they instantly hand you a little paper ticket, that's your 202 accepted response. You walk out.
And you get a text message 3 days later when the clothes are clean.
Exactly. It completely decouples the user experience from the processing time.
But the second category in our matrix is transport routing. Because if the API just hands out a ticket and closes the connection, how does the suit actually get cleaned? How does the PDF get generated?
The blueprint architecture details a fascinating pipeline here. It uses the Symfony message bus and a Redis stream. Walk me through the exact handoff.
When the API dispatcher receives a validated DTO for an operation marked as asynchronous, it does not call the lazy proxy.
Instead, it wraps that DTO into an envelope.
This envelope is a message object. It then hands that message to the Symfony message bus.
The internal post office of the framework.
Right. The message bus reads the routing configuration, sees this message needs to be processed in the background, and pushes it out to a transport layer.
And for high-performance systems, this transport is almost always Redis, specifically Redis streams.
Now wait, why Redis? Why not just insert a row into a MySQL table called background jobs and have a script read from that? It seems simpler.
Using a standard relational database for high-throughput queuing is a recipe for deadlock and performance degradation.
Relational databases use row locks. If multiple workers try to claim the same job from a table simultaneously, they block each other.
Redis, however, is an entirely in-memory data structure store. It is blindingly fast.
And Redis streams are specifically engineered for this exact problem. They use consumer groups to guarantee that a message is delivered to exactly one worker, autonomically, with zero locking overhead.
So dumping a message into a Redis stream takes fractions of a millisecond.
Okay, so the API drops the message in the Redis queue and returns the 202 ticket. Who is on the other end of that queue picking up the work?
This is where we look at asynchronous topologies. On the other end of that Redis stream are supervisor demonized workers.
Demonized workers.
These are completely independent PHP command line processes. They run constantly in the background of your server infrastructure.
Managed by a program like Supervisor, which ensures they stay alive and restarts them if they ever crash.
They don't know anything about HTTP. Their only job is to run a command, usually Messenger consume, which continuously listens to the Redis stream.
Like little robotic assembly arms constantly checking a conveyor belt.
Any new PDFs to generate? Any new PDFs to generate? Yes. And the architecture allows you to create highly optimized topologies. You don't just have one queue. You can have a high priority queue and a normal priority queue.
And as a developer, you control this entirely through metadata.
You just add an attribute to your operation class.
Operation metadata background is a new background object with delay 300, priority HIGH.
The elegance is unmatched. By simply adding that one attribute, the framework knows to route this operation's message to the high-priority Redis stream. You can even tell it to delay execution. Maybe you want an abandoned cart email to wait precisely 1 hour before sending. The message bus handles the temporal delay perfectly.
Okay, but as a skeptic, I have to point out the third category in our matrix: error handling.
This all sounds great when it works. But in a synchronous request, if the database connection drops while I'm creating a user, the framework immediately catches the exception and returns a 500 internal server error to my browser. I know it failed.
With async, I've already walked away with my dry cleaning ticket. The API said everything was fine. What happens if the background worker crashes while trying to render the PDF? Is my data just gone forever?
In a poorly designed system, yes. But an enterprise-grade message bus builds robust resilience into the asynchronous pipeline. The first line of defense is exponential backoff.
How does that work in practice?
If the worker throws an exception, maybe a third-party API is momentarily down, it doesn't just discard the message. The framework catches the failure and tells Redis, this failed, but don't delete it. Put it back in the queue, but make it invisible for exactly 5 seconds.
Giving the network glitch time to resolve itself.
Right. And if it fails again, it waits 15 seconds, then 60 seconds. The retry delay grows exponentially. It automatically handles transient failures without any human intervention.
But what if it's a hard bug? What if there's a typo in the PDF template and it will never succeed no matter how many times you retry it?
That's the second line of defense. After a strictly defined number of retries, say 3, the worker gives up. But it still doesn't delete the message. It routes it to a dead letter queue.
The graveyard for broken messages.
Exactly. This is usually a dedicated doctrine transport and actual database table. The failed message, along with the complete stack trace of the error, is serialized and safely stored there.
So an engineer can wake up the next morning, review the dead letter queue, realize there's a typo in the code, deploy a hotfix, and then literally click a button to replay the failed messages.
The PDF generates, and the user's data is never lost.
It guarantees zero data loss, even during systemic infrastructure failures. But this brings us to the final category: user feedback.
We've solved the back-end processing, but we've created a massive user experience gap.
The user has their ticket, but how do they know when the job is actually done? We can't return JSON to their browser. The connection closed 10 minutes ago.
Right, how do we close the loop?
The architecture defines a post-execution pipeline. When a background worker finally succeeds, the PDF is generated and saved. It fires a specific event into the internal event dispatcher, an operation performed event.
And this event carries all the context. It contains the original input DTO, the output result, and the operations metadata.
Sitting quietly in the background is an event subscriber, specifically an operations subscriber paired with a service locator.
It listens for every completed operation.
It inspects the metadata to see if this specific task required user feedback. It looks for a flag like requires notification set to true.
And if it sees that flag, what does it do?
It uses the service locator to lazily load a specific notification handler. Maybe it's a Twilio SMS integration or a WebSocket pusher or an email client.
It hands the result to the handler, which sends the text message. Your invoice is ready to download.
It seamlessly bridges the asynchronous backend processing back to the synchronous human experience. It's beautiful.
Okay, we are entering section 7, master synthesis and scale. We have covered an immense amount of ground. We've looked at the gears, the locks, the memory optimization, and the temporal shifting.
Let's pull this all together. Let's trace a single, highly complex request flowing through this entire ultimate operation pipeline. A master synthesis.
Let's use a challenging scenario. Let's say we have an e-commerce API and a user is checking out. They want to apply a loyalty discount.
Okay.
But let's say this user is malicious and they are trying to manipulate the payload to trigger a warehouse inventory change instead.
A classic contextual privilege escalation attack.
Oh.
Okay, let's trace the microseconds. The raw HTTP request enters the infrastructure.
Instantly, before Symfony even fully boots, the rate limiter intersects it. It checks the Redis token bucket. The user hasn't exceeded their limit. A token is decremented atomically. The request is allowed to proceed.
Then the request hits the security firewall. The stateless authenticator pulls the JWT from the XAuth token header. It mathematically verifies the HMAC signature using its in-memory secret key.
The token is valid. The identity is confirmed as a standard user. No database query required.
The request moves to the routing adapter. The controller looks at the URL, say /AP/v1/checkout/discount, and translates it into an AP input object, targeting the apply loyalty discount operation, wrapping the malicious JSON payload.
Now the contextual isolation kicks in. The kernel interceptor inspects the route. It sees the endpoint belongs to the e-commerce domain.
It checks the apply loyalty discount operation. That also belongs to the e-commerce domain. The boundaries match.
The payload enters the core dispatcher. The AP operation handler utilizes the tagged iterator to instantly find the lazy proxy for apply loyalty discount without loading its massive pricing engine dependencies.
The dispatcher attempts to deserialize the JSON into the strictly typed apply loyalty discount input TTO, and here's where the attack fails.
The user tried to include inventory override set to true in the JSON, but because the strictly typed DTO doesn't have an inventory override property, the Symfony serializer completely ignores it. The malicious data is stripped away instantly.
The sanitized DTO is then passed to the declarative validator. It applies the dynamic validation by role. It confirms the user has provided a valid discount code string. The DTO is mathematically proven to be valid.
The dispatcher then makes its final security check. It calls the operation voter, is granted perform on the operation.
The voter confirms that a standard user is allowed to apply a discount to their own cart. Authorization granted.
Finally, the dispatcher checks the temporal metadata. Is this operation synchronous or asynchronous?
Applying a discount requires immediate feedback to recalculate the cart total on screen. It is synchronous.
So the dispatcher finally invokes perform on the proxy. The proxy materializes the heavy pricing engine, executes the complex business logic, calculates the new total, and returns the standardized API output.
The adapter layer transforms that output into a JSON response, sets the HTTP 200 OK status code, and sends it back to the client.
The entire gauntlet rate limiting, stateless authentication, context verification, strict sanitization, dynamic validation, role-based authorization, and business execution completes in a matter of milliseconds.
It is an absolute masterclass in defensive high-performance engineering. And this architecture doesn't just shine in e-commerce. Think about social media systems.
In a social media environment, handling millions of granular actions per minute, liking a post, sharing a link, the asynchronous topology is what keeps the platform alive.
The critical action recording the like, so the user sees the heart icon turn red, executes synchronously.
But the massive weight of analytics, updating trending algorithms, notifying the content creator, pushing the interaction into a data lake is entirely decoupled.
The dispatcher just throws an interaction occurred message onto a normal priority Redis stream. Right. The user gets their instantaneous response, completely shielded from the heavy lifting happening in the background demons.
Or consider IoT telemetry, the Internet of Things. If you have 10,000 temperature sensors pinging your server every second, a traditional monolithic MVC framework would choke on the memory bloat of instantiating full controllers and services for every single ping.
But with this operation-oriented engine, the controllers are just tiny adapters. They wrap the ping in an AMP input, validate the telemetry DTO, and either drop it in a Redis queue or execute a highly isolated, lazy-loaded operation.
It handles the volume because it only hydrates exactly what it needs, exactly when it needs it. We have taken a massive journey today.
We really have.
We started by dismantling the ambiguity of standard CRUD endpoints, where simple data updates mask dangerous business side effects.
We introduced the operation-oriented paradigm, mapping API capabilities directly to ubiquitous business language.
We fortified those operations with impenetrable, strictly typed DTOs and declarative validation. We solved the monolithic memory crisis using dependency injection proxies to keep thousands of operations lazily sleeping until the exact microsecond they are needed.
We built a transport-agnostic central dispatcher, protected it with stateless firewalls, atomic token buckets, and contextual interceptors.
And finally, we bent time itself, routing heavy tasks through Redis streams and background daemon workers with exponential backoff.
It fundamentally reshapes how we view API development. Architecture is no longer just a structural requirement to make code run. It becomes a physical manifestation of business intent.
It actively protects and enforces the rules of the organization at the deepest, most foundational layers of the stack. Which leaves us with a profound shift in perspective to think about.
When you build a traditional CRUD API, your database is just a ledger of current states. You know what the data looks like right now.
But when you build an operation-oriented API using this blueprint, every endpoint, every message queue, every log file is permanently recording why things change.
You aren't just logging state, you're logging human intent.
And that raises a fascinating question for the systems we build tomorrow. If our systems shift from tracking what changed to permanently understanding what specific intent caused the change, how does that revolutionize our ability to audit, to debug complex distributed failures, or to use machine learning to understand the true behavior of our users?
You are no longer mining passive data. You are analyzing a living history of intentional action.
It turns an API into a semantic engine. We hope this deep dive has given you some powerful, concrete mental models to bring to your next architecture planning session, whether you are untangling a legacy monolith or designing a massive, scalable microservice ecosystem. Thank you so much for joining us on this deep dive, and we will catch you on the next one.